Okay, let's get started. So welcome back. We're going to start off with an example. So last time we were talking about, now we're in polar coordinates and we're looking at these double integrals. We looked at a few different cases where we defined this polar rectangle, and then we started going to more arbitrary domains. And then we looked at some examples where perhaps we couldn't even do them in Cartesian. The integrand didn't have an elementary antiderivative in Cartesian coordinates, but when we translated it to polar coordinates, we were able to do the integrals without really a problem. So we're going to do, I think, 2 more examples in this section, and then we're going to kind of move on to 12.4. So to get us started, let's jump right in. We're going to find the volume of the region that lies under the sphere which we write as x squared plus y squared plus z squared is equal to 9. Above the plane z equals 0, and inside the cylinder x squared plus y squared is equal to 5. Okay, so take a deep breath. It might look kind of bad right now, but let's break it down. What's really happening? So maybe kind of picture this from the side. I have some plane, z equals 0. So in fact, this is the xy plane. And then I have some sphere with radius 3. So maybe it looks something like this. And then I have a cylinder that in the xy plane has a radius that is smaller than the sphere. So maybe we have some kind of cylinder like this, right? And we're trying to find this volume. Okay, so we're going to have a cutout of this cylinder in the xy plane. This cutout is our region R. And then the z, the height is this from our plane, z equals 0, up to the sphere. So the sphere defines our integrand, but the cylinder is going to define our bounds. So let's also kind of just put this into text. The cylinder equation gives us that the region R is the set of all points such that x squared plus y squared is less than or equal to 5, right? So it's inside our cylinder. In polar coordinates, We can instead write this as all the points in R and theta such that theta goes from 0 to 2 pi, and R goes from 0 to the square root of 5. Right? Because that's what this means. This is a circle of radius square root of 5, and we want to have this entire circle. Okay. Now, the surface of the sphere is, we can write this as a function of x and y, so we can solve for z. This is the square root of 9 minus x squared minus y squared. And we make sure that we choose the positive version of our radical because we want the top half of that sphere. But this is in Cartesian coordinates, right? If I'm going to do my integral in polar, I have to convert this as well. Well, lucky for us, this x squared and y squared is actually pretty nice. So notice that we can actually write it like the square root of 9 minus the quantity x squared plus y squared. And we know that this is r squared. So in polar coordinates, this is 9 minus r squared. So if we're looking down at our volume, our region R was just a circle of radius root 5. So we can finally write down our integral. So the volume of this is the double integral over R of the square root of 9 minus r squared dA. Now we can actually put bounds here. And I'm going to do dr d theta. And we can't forget our r here. So in polar coordinates, remember our dA looks something like this, where we have this extra r. So if I'm doing my radius first, this goes from 0 to the square root of 5, and theta goes from 0 to 2 pi. Under the radical, could you plug in 5 for r squared? No, we can't, because r here is not a constant. The square root of 5 says that you're only on the edge of this circle. That is not the case when we're doing this, because we have to go across and integrate along or across the circle. So we're doing this. Remember, we're going from r equals 0 all the way out. If we stuck and said that r was root 5, we would only be doing the outside of the circle. We need to do the entire region. So we can't just sub in root 5 for r here. Okay. So this is actually a u substitution that we can perform. So on the side here, let's have that u is equal to 9 minus r squared, or that du is equal to -2 r dr, right? And we can solve for this r dr because this is what actually shows up right here. So -1/2 du is equal to r dr. So we can rewrite our integral. Our thetas remain the same. We'll do the bounds in a second here. We have that this root now becomes u to the 1/2. In a negative, well, we have that this is just u to the 1/2, but then we also have that r dr is -1/2 du, and we still have our d theta. And now we can work on the bounds here. When u is 0, or sorry, when r is 0, so we go ahead and plug that in. We plug in 0 for r, and we notice that u is 9. And then when we plug in √5 for r, we get that u is 4. So we can keep going. You can actually pull out a negative and swap them if you would like. So this we can actually write as 0 to pi, 4 to 9, and then we get a negative. So we get rid of that negative that's in our integral or integrand. So u to the 1/2 du d theta. Okay, so we're continuing. Let's do the u integral first. We get 0 to pi. And this gives us, when we bump this up a full power, we get 3/2, and we have to divide by 3/2 or multiply by 2/3. So we get 1/3 u to the 3/2. And we're evaluating this when u is equal to 4 and u is equal to 9. And we still have our d theta. So this is the integral from 0 to 2 pi. We can plug these in. We end up with 19 over 3 du. And then we'll get a 19 over 3 times theta evaluated at 0 and 2 pi. So it's much like just multiplying this by 2 pi. So we get a 38 pi over 3. And that's the volume of this object that was kind of contained by the sphere and the cylinder, as well as the z equals 0 plane. So even though the text looked like there was a lot, right? There's 3 different surfaces going on here. Just sketch it out. See what it looks like. Kind of think about it in R3. So here, the first thing we did was, okay, I have a sphere. I have the z equals 0 plane. And then I have some cylinder that kind of cuts through this. And then this is kind of the shadow that our volume casts onto the xy plane, right? So this is going to be the region that we integrate over, and our z component is dictated by the sphere. What if the region wasn't a circle and it was an ellipse? Instead, how would you set the bounds for polar conversion? Ooh, if it was an ellipse, the answer to this is either we're going to talk about substitution that goes beyond u substitution. So u substitution is kind of like this 1D thing. We're going to talk about how to do like a u and v substitution, because now we're working with 2 dimensions for these integrals. That's one way to do it. You can translate the ellipse to a circle in like uv space rather than just r or xy space, whichever. So you can make it into a circle that way. Or if you want to do polar coordinates, strict polar coordinates, it's really tough. You might have actually a better time doing Cartesian. But we will talk about how to do a UV substitution and kind of translate. So if this was an ellipse rather than a circle, we would go ahead and make it into a circle. But otherwise, we would just simply try to do Cartesian coordinates. You can try to do halves, or you can try to dictate the function r as a function of theta. That would also work if you want to stick with polar coordinates. So if you have an ellipse, let's kind of just do a sketch here. If you wanted to do like an ellipse, you would have to find out how r changes with theta. So r would go from 0 out to that function of theta that dictates this perimeter here, instead of a constant value. And that was kind of the idea of the general region that we talked about yesterday. Okay. Oh, it was a lengthy explanation. So now let's get some practice with converting different coordinate systems. So find the integral from -1 to 1, the integral from negative root 1 minus x squared to 0 of cosine of x squared plus y squared dy dx. Okay, there is no way that I'm going to try to do this in Cartesian coordinates. The way that it's written, I don't want to do it. That looks messy. What I can do is try to see if I can convert this to a different coordinate system, polar coordinates, right? So the idea is we need to get practice at looking at these integrals and knowing what is kind of being portrayed by them. So this looks pretty gross. So in fact, let's kind of write out the domain in Cartesian coordinates. So maybe this is over some region we'll call D. And it's all the sets of x and y such that, now notice that this ordering here helps us determine what's going to what. So x goes from -1 to 1. And we know that y goes from negative square root of 1 minus x squared to 0. Okay, so what does this look like? What does this region look like in the xy plane? Let's go ahead and just kind of do our little sketch here in the xy plane. Well, x goes from -1 to 1. So it looks like we're going from maybe -1 to 1. And then y goes from negative, so we can actually go ahead and write this out to find the boundary. Negative square root of 1 minus x squared is equal to y. So you would square both sides, and then you get 1 minus x squared is equal to y squared, or that x squared plus y squared is equal to 1. So this is the unit circle centered at the origin, but the negative here tells me that it is the lower half, right? So I have the lower half of some circle, and then I go up to y equals 0. So it looks like this is my region D. So it's good to get practice looking at this and figuring out what the domain is and what it looks like. Okay, so in polar coordinates, let's write our region D as the set of all points r and theta. Now, there's a few different ways that I could write this. I'm going to have theta go from, this is negative pi, and this is 0. So I'm going to go from negative pi to 0. You could have also done pi to 2 pi. That's also fine. And then r, because this is a unit circle, this looks like an ellipse, but it's a circle of radius 1. We know that r goes from 0 to 1. So now we can set up this integral. Instead of having this messy Cartesian integral, what we could do is now write it as our polar integral. So we had cosine of x squared plus y squared. Well, that is just r squared. And then we'll have our dA. So we have r, and in this case, we're going to go dr d theta. And r goes from 0 to 1. And theta, we said, in this case, goes from negative pi to 0. You could have also had, pi to 2 pi like we talked about earlier. Okay, so let's go ahead and do this out. Well, this is another u substitution. So this time we're going to let u be r squared. So we have 2r dr is equal to du, or that r dr is equal to 1/2 du. So our integral, therefore, is negative pi to 0. And then we're doing our u integral. So this is cosine of u. And our r dr became 1/2 du. We still have our d theta. Now let's work on the bounds here. When r is 0, u is 0. And then when r is 1, u is 1. So we can do this integral. We got negative pi to 0. It says 1/2 sine of u evaluated at u equals 0 and u equals 1 du. Sine at 0 is 0. Sine at 1 is just sine of 1. So I'll have the integral from negative pi to 0 of 1/2 sine of 1 d theta, or pi over 2 of sine of 1. So instead of doing it really messy using these Cartesian coordinates, we looked at the bounds, looked at the ordering of dy dx, and we figured out the region that was being integrated over. We realized that this might be a lot better in polar coordinates, so we translated, and our integrand actually became pretty nice in polar coordinates as well. So definitely kind of expect problems like this on the homework or quizzes, or maybe even like an exam. You look at this set of integrals and you're able to convert from one coordinate system to the other. So get familiar. Like I said, we really have to lock down these basics. How do the bounds define our regions? How do we find these bounds? Can you reverse engineer what the region looks like, right? So that's the core of this whole chapter, are the bounds. How do we do this? Okay, and that ends section 12.3. Now let's jump in. Let's go to a new page. We're going to talk about 12.4. So 12.4 is applications of double integrals. So now that we've kind of discussed double integrals, what can they be used for other than volume, right? We've learned in the past that integrals can be used for things like arc length, calculating work done. We've seen even stuff like, center of mass. So let's kind of extend some of these ideas to higher dimensions. So we're going to start with density. And mass. So again, the idea here is that we're going to break up the thing that we really want to calculate to approximations and see how integrals kind of form from there as we get better and better approximations. So imagine a thin plate that occupies a region D. On the X, Y plane. And it has variable density. In units of mass per unit area. And it's given by some function rho. In a lot of different fields, these densities have so many different definitions, being like, what Greek letter do you choose? I've seen sigma, I've seen delta, I've seen rho, bunch of stuff. But as long as you know what the density function is, then it's fine. I think physics a lot of time dependent on if you're talking about density on a line, density on a surface, or density from a volume, they all use different Greek letters. But as long as we're kind of consistent here, the density that we're going to be talking about is rho, I think we're fine. So in the region D. I think your book might do something else as well. In a given rectangle, around point X, Y, the density is approximately how much mass is in that rectangle divided by how much area is in that rectangle. So imagine that we have maybe some kind of general flat plate that looks like this. And I'm going to take a little snippet of it and I get some rectangle. So it has some mass to it. And it also has some area to it. Well, I'm going to approximate the density in this rectangle. So in fact, the ratio of these two approaches the actual density as the rectangle gets smaller. And that makes sense. If I have some rectangle around this point and I wanted to know the density at that point, if I choose a large rectangle, I'm going to have a bad approximation. But as I let that rectangle get closer and closer and closer, smaller and smaller to that point, right, I get a better approximation of this density. So the idea here is we're not really trying to approximate density because density might be given to us. But what we can do is use this to rewrite and find an approximation for the mass. So the mass on that little rectangle is approximately the density function that we're given and the area of that rectangle. Right? So all I did was just multiply over this area, right? So I can kind of approximate that the mass in this rectangle is the density at that point multiplied by the area. So this kind of sounds a lot like what we were doing, right? This point is our sample point, and I have some area here that I am using with this rectangle. But as I kind of let that rectangle be smaller and smaller, right, this mass becomes more accurate because the density is more locally defined here by that point, that sample point. So if this is the mass of that one rectangle, what I could say is the total mass is then some Riemann sum. Where I have the density at my sample point times the area of each of those rectangles. And we've seen this. This looks exactly like how we were doing double integrals. So in the limit, we get that the mass is equal to the double integral over the region D of the density function dA. So again, we're using these integrals as sums, right? We're adding up the mass on each of these really small areas with a density function. So we have some density times some really small mass there, and we add, or sorry, small area there, and we add those all up, and then we get this mass, right? So let's keep thinking about these integrals as these sums. I'm adding up all of the density times some area to give me this mass. You don't even have to think about this as like mass in terms of like matter. You could also think of it as any type of density. If you have density of an electric charge, instead of finding the mass, you could find out, you know, the electric charge that you have. The mass can be used for both Cartesian and polar coordinates. Correct, right? I didn't write either case here. I didn't say that this was a Cartesian setup or a polar setup. We did use rectangles to get us there, but we could have also done polar rectangles. Yeah. So the idea here is this is the generic double integral. This doesn't have a specificity of Cartesian or polar coordinates. Okay. So next, let's talk about center of mass. So in Calc 2, you learned how to do the center of mass, but we're going to kind of, elaborate more on center of mass in higher dimensions, as well as maybe we have like some weird object, right? So before you might have had like a really nice object where maybe it was just like here and it was just this guy. Let's find the center of mass. Okay, that's great and all, but what if my object, looks something like this? How do I find the center of mass of this guy? We might have to use double integrals or something like that. Okay. So in Calc 2, we defined the moment for a particle about an axis as the mass times the distance to that axis. And that's how you kind of came up with these definitions for center of mass in Calc 2. Is you looked at the moments for specific points, and then you accumulated all of those points, and then you have the center of mass or the moment for the entire object by treating each individual point separately. So let's kind of do that thing again. Let's do that same type of analysis here. So the moment about the x-axis of a small rectangle on our region D is approximately the mass times the distance. So the mass here is our density function at the sample point times the area of that rectangle. The distance from the x-axis is the y value at our sample point. So now the idea here is this is now the moment of that small rectangle. And if I wanted the moment of the entire object about the x-axis, I would add all of these things up. So if we add up the moments of each rectangle, we approximate the total moment. In the limit, we can say that about the x-axis, we have the x moment. This is the double integral over the region D of y times the density of x times y dA. Right? And that's just translating what we have here. We have the density times the distance from the x-axis, which is y, times this area term. So now we could have done the moment about the y-axis. And you can imagine, looks very similar, except now we have an x rather than a y times our density, because this is now the distance from the y-axis. So same as Calc 2, the center of mass which typically they use x bar and y bar. So this is the exact coordinate. Bars typically mean averages, so it's kind of like an average here. So the center of mass at x bar, y bar is given by x bar is my over m, where this little m is in fact our mass, and y bar is mx over m. So we can actually sub in our definitions in integral form. So x bar is the double integral over d of y, or my, which has an x, over the mass, which is the double integral over d of just the density. And then y bar, almost the same thing, except we get a y here. So this is our integral form. Okay. Let's do, oh yes, let's do moments of inertia. Okay, so this was finding the center of mass for a general region. Now let's talk about moments of inertia. The moment of inertia or sometimes called the second moment of a particle that has mass m about an axis is mr squared, where r is the distance to that axis. So if we treat each small rectangle as a particle, each moment of inertia is, when I do know we're should be in time for a break soon, so let me just finish this up and then we can take our 5-minute break. So the particle, yeah, so if we, in each small rectangle as a particle, each moment of inertia is therefore on the x-axis, we have the mass, which again is our density at our sample point, times the area of our rectangle times the distance to that axis squared. So now this time we have a y squared. The y-axis, very similar. We have our density, times our area. That gives us our mass. And then the distance to the y-axis squared. So we have an x squared here. There's one more. This time we actually also consider about the origin. Which in this case we still have our mass. But now we have the distance from the origin, which is our x squared plus our y squared. Okay, why don't we take our 5-minute break there, and then we'll continue this, and we'll turn these into integrals. Okay, so let's continue. So our discrete approximations for the moment of inertia about the x, y, and the origin, or our mass given by our density times our area times the distance to that axis squared. So if we add up all of these approximations for each of these rectangles, then of course we get an approximation for the total moment of inertia. And in the limit, we can write down that the moment of inertia given by capital I about the x-axis is the double integral over the region D, y squared, and then the density function times dA. About the y-axis, the moment of inertia is therefore the double integral over the region D of x squared times our density function, dA. And about the origin, this moment of inertia, just subscript O, is the double integral over the region D of x squared plus y squared times our density function times dA. So you might be asking yourselves, what is the moment of inertia, right? It's kind of like mass in the rotational setting, right? So if you start thinking about like angular momentum and you have an object spinning on a certain axis, these are the guys that you want to look at. So if there's huge tables that you can look up, oh, if my object is uniform density and it's like a cylinder, and it'll tell you, oh, I'm rotating it around like this axis, it will give you the moment of inertia for that. But how those are calculated is via this way, right? So if I have some moment of inertia of some kind of thin plate and I'm rotating it about some axis, we can do it like this. Now these are just for two-dimensional things. We will get to a third integral, do triple integrals, but let's hold on that just for a little bit longer. Okay. So that's both center of mass as well as moments of inertia. So let's start diving into some examples. So a little word problem here. A thin plate covers the triangle region bounded by the x-axis and the lines x is equal to 1 and y is equal to 2x. In the first quadrant. The plates density is given by a function of x and y that is 6x plus 6y plus 6. Find the plates center of mass. Okay. So the first thing to do, sketch the region, right? I have got this triangle and it's bounded by the x-axis and the lines x is equal to 1 and y is equal to 2x. And it's in the first quadrant. So let's figure out what our domain D or R, whatever you want to call it, is. So we're in our first quadrant. We have some triangle. Perhaps looks like this. This is our region D. X and Y. This is y is equal to 2x, and here we have x is equal to 1, and down here we have that y is equal to 0. Okay, so we can start thinking about this like if I want to do this in Cartesian coordinates or I want to do this in polar coordinates. Well, looking at this, I probably want to do Cartesian, and I can also think about, oh, what type is this? I can either do type 1 or a type 2, right? So I can either do, I go across here horizontally and then add up the traces in this direction, or I can do vertical traces and then add up all those vertical traces. That also works. So if we're trying to find the center of mass, we need the mass, right? We need to know what the total mass is, and then we can find the moments accordingly. So first, let's kind of figure out the mass. Remember, the mass is the double integral over d of the density, dA. Okay, so let's set up a double integral here of our density function, which is 6x plus 6y plus 6. And I'm going to choose to do dy dx. So now I have to look back up at my region and figure out what I have to do here. So y, just so I'm doing these vertical traces and then adding up all those vertical traces. So I look at my vertical trace. It goes from y equals 0 all the way up to y equals 2x. So this goes from 0 to 2x. And then x is the range of those traces. So it goes from x is equal to 0 all the way over to x is equal to 1. So this goes from 0 to 1 here. So we can do our double integral. This is the integral from 0 to 1. This is 6x times y plus 3y squared plus 6y. Y is equal to 0, and y is equal to 2x dx. So we have the integral from 0 to 1. And I plug in, notice there's a y on every single term, so if I plug in y equals 0, I don't get that second term at all. But I do get contributions from this first term. I get a 12x squared plus a 12x squared plus a 12x dx. So I got a 24x squared here. So I can go ahead and integrate this. This will give me an 8x cubed plus a 6x squared, x equals 0, and x equals 1. So I can plug those in, and I'll end up with 14. So it looks like the mass here is 14. So to find the center of mass, I need to find both of the moments. I need to find the x moment and the y moment. So let's go ahead and calculate those. So let's do mx first. So this is going to be over the same domain. So I probably don't need to really mess with the bounds too much. But remember, this is now y times our density, which is 6x plus 6y plus 6. Still going to do dy dx, which means that my bounds, because I'm over the same region, are the same. So now we have to do this set of integrals. So this is 0 to 1. This time I get 3x y squared plus 2 y cubed plus 3 y squared, evaluated at y equals 0 and y is equal to 2x dx. So this is the integral from 0 to 1. Notice again, if I plug in 0, I don't get any contribution from the second term. So all I'm really thinking about is plugging in y equals 2x. This ends up giving me a 28x cubed plus a 12x squared. Right, because I get an x cubed from this term, but I also get an x cubed from this term here too. So I can go ahead and integrate this. This is 7x to the 4th plus 4x cubed, evaluated at x equals 0 and x equals 1. plug in x equals 0. I don't get any contributions from that, so we can just go ahead and plug in 1. That's pretty easy. I get 11. All right, so that was the x moment. Let's look at the y. Again, we have a double integral, but this time we have an x times our density. So 6x plus 6y plus 6 dy dx. And because we're over the same region, shouldn't really mess with our bounds, going from 0 to 2x and 0 to 1. So we have the integral from 0 to 1 of 6x squared times y plus 3y squared times x plus 6 times x times y. Y equals 0 and y equals 2x dx. So again, notice if we plug in y equals 0, they all have these y terms in them, so they doesn't contribute at all. So all we're really thinking about is plugging in this y equals 2x, and I end up with 24x cubed plus 12x squared dx. So this ends up being, once I integrate, 6x to the 4th plus 4x cubed, x equals 0, and x equals 1. If I plug in x equals 0, I don't get any contribution from that second term. So I'm thinking about just plugging x equals 1, and that's just 6 plus 4. So then I'll get a 10. Okay, so now we've calculated all the things that are necessary to find what the center of mass is. So x bar, remember, was my over the total mass, which is then 10 over 14. And then y bar was mx over the total mass. So we get 11 over 14. So the center of mass is, we can simplify this a little bit. This is 5/7 over 11/14. Okay, so longer example, right? We had to calculate all three of these sets of double integrals, but it gives us the center of mass of this object. Okay, so let's keep going. Let's do another example. We're going to find the moment of inertia for our previous we're going to do actually moments of inertia for our previous plates. So again, our previous plate looked like this guy here. So we have this triangle. In fact, why don't we just sketch it down here as well? So we have y equals 0, x is equal to 1, and y is equal to 2x on our x and y plane. So we're going to try to find all of the moments that we've discussed here. So the first thing to do is look about the x-axis. I'm going to use the same bounds. This is the same region after all. But this time I have a y squared times my density. So a 6x plus 6y plus 6 dy dx. This is the integral from 0 to 1. So now I'm integrating with respect to y here. So I get a 2 times x y cubed plus a 3/2 y to the 4th plus a 2 y cubed. Y equals 0 and y equals 2x dx. We still have our x integral from 0 to 1. So we're plugging in these. Again, we've got a bunch of y terms, and we've got this y equals 0. So that looks like that second term doesn't contribute. So we just think about plugging in y equals 2x. So we're going to get a y to the 4th from here. And we're also going to get a y to the 4th from here. And those together end up giving us a 40 times x to the 4th plus 16x cubed dx. So we can integrate this nice polynomial. This gives us 8x to the 5th plus 4x to the 4th. X is equal to 0 and x is equal to 1. So we've probably got it to the point where, yeah, we plug in the 0, we don't get any contribution from that term there. So we're plugging in x is equal to 1. So it ends up being just 12. Okay. So now let's do about the y-axis. So we're over the same region. But this time in our integrand, we have this x squared times our density. So we still have our 6x plus 6y plus 6 dy dx. Okay. So we can do our y integral. So we still have our x integral left from 0 to 1. And then here, what we're left with is a 6x cubed times a y plus 3x squared y squared plus a 6x squared times y, evaluated when y is equal to 0 and y is equal to 2x. Man, it's been sure nice that this y is equal to 0. We can plug that in again and we don't get any contribution from that second term. So we go from 0 to 1, and now we're just thinking about plugging in this 2x here. So we're actually going to get x to the 4th contributions from this term as well as this term. And here we've got a 24x to the 4th plus a 12x cubed dx. Or we can integrate this out and we'll get a 24 over 5 times x to the 5th plus 3 x to the 4th when x is equal to 0 and x is equal to 1. So we can plug those in and we end up with 39 fifths. And they've all been such nice integers at this point. It's kind of a shame that it didn't work out for the y moment. All right, so the last thing for us to calculate is about the origin. Now we actually don't need to do that full integral because we already have all the necessary information. So recall that this was x squared plus y squared times our density function times dA. Well, I can write that as x squared times my density plus y squared times my density dA. And we know that this is a linear operator. Meaning that we can separate these integrals and do them separately. So y squared times our density dA. Well, this just means that we have iy plus ix. And we have already calculated both of those things. So for our problem, this is 12 plus 39 fifths, which ends up giving us 99 fifths. Okay, so we've got about 10 minutes left. I think we can finish up. So the radius of gyration. So the radius of gyration about an axis is the number r such that the mass times the radius squared is equal to the moment. So remember, the moment of inertia for a particle was m times r squared, right? And when we do this over like a generic region with variable density, obviously it doesn't just become mass times radius squared, because each moment is considered differently. We add all of those things up. So now it's acting as if what is the r that makes this weird object seem like a particle? So that's kind of what's happening here. How can I relate what is the radius? What is this r value that needs to take place so that I can treat this weird object like a particle? So in particular, the radius and this they actually use y double bar for these, with respect to the x-axis and x double bar with respect to the y-axis so m y double bar squared is equal to ix, and m x double bar squared is equal to I y. The point x double bar y double bar is where the mass can be concentrated without changing the moments of inertia. Moments of inertia. So it's just like center of mass, right? If you calculate the center of mass, and that just kind of represents if you concentrated all of the mass of that object at that point, the center of mass doesn't change, right? Like the moments don't change. This is the equivalent. So here we have it's kind of like the center of moments of inertia, right? So here, for example, I guess for our example, the one that we've been doing today, x double bar is equal to the square root of Iy over m, which was the square root of 39 over 70. That can't be right. What was our mass? Our mass was 14. I don't know why I have 70 there. Over 14. And then we have y bar, which is the square root of ix over m, which is the square root of, and I think we got 12, right, for ix. Let's kind of go up here. Yep. And then mass was 14, so we can reduce this to 6 over 7. Okay. There's one last question, and then we can take off. Is this gyration an application we should expect to see elsewhere, homework, quizzes, or an exam? Sure. Yeah. So you might have a question that's like calculate, the radius of gyration, or find, x double bar, y double bar for a particular object, right? Just like, finding the center of mass, you would need to calculate x bar, y bar, and then the mass here, you would need to calculate, the moments of mx, my, and the mass to find x bar and y bar. These double bars, you would have to calculate the moments of inertia for iy and ix, as well as the mass. Oh, right, it was 39 over 5, right. You're right. So it was 39 over 5 over 14. There we go. All of them were such nice integers, I forgot that one was a fraction. There we go. Thank you. Okay, so that wraps up today. We're actually done with 12.4. So we're a little bit ahead. We're going to start triple integrals tomorrow. And then on Friday, we have no class. So I'll see you all tomorrow. Until then, stay safe.